Tonight, we're going to travel to a place no human eye has ever seen and no spacecraft has ever been designed to reach. A place so far from everything you know that the sun itself, that burning star that warms your face, that lights your morning, that has anchored every civilization in human history, shrinks to nothing more than a faint point of light, indistinguishable from the thousands of other stars scattered across the dark. Tonight, we're going to stand together at the very edge of our solar system. And what NASA found waiting there is something that quietly, permanently changed the way scientists understand where we live in this universe. Here is what most people never stop to consider. The solar system does not end where the planets end. Neptune, the last of the great worlds, orbits the sun at roughly 2.8 billion miles away. That number sounds enormous, and it is, but it is only the beginning of the distance. Beyond Neptune stretches a region so vast, so ancient, and so poorly understood that the most powerful telescopes ever built can only guess at what fills it. The true edge of our solar system lies not billions, but trillions of miles from where you're lying right now. And for decades, we sent two small machines into that darkness. Machines the size of a small car, running on less power than a refrigerator light. And we waited. We waited for them to tell us what was out there. What they sent back was not what anyone expected. By the end of tonight, you're going to understand exactly why the edge of our solar system is one of the most mysterious, most scientifically contested, and most quietly terrifying places in the known universe. You are going to understand what NASA's Voyager spacecraft actually detected the moment they crossed the boundary between our sun's reach and true interstellar space. You are going to learn about a strange ribbon of energy encircling our solar system that no one predicted and no one has fully explained. And you're going to sit with a possibility that very few people ever pause long enough to consider, that our solar system may be surrounded by something vast and structured, something pressing in from the outside, something we are only now beginning to have the instruments to measure. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. There is a moment when you're falling asleep, where the world around you begins to dissolve. The sounds of the house fade. The weight of your body softens into the mattress. And for just a second, before sleep takes you completely, you become aware of how small and quiet everything is. I want you to hold on to that feeling tonight, because that is exactly the feeling I want to guide you with as we begin this journey together. Not anxiety, not urgency, just a slow, open awareness of how vast the darkness truly is. Let us start with something familiar: the sun. You know it. You have felt it on your skin every day of your life. It rises, it arcs across the sky, it sets. It is the most constant thing in your world, and yet most people go their entire lives without ever truly grasping what the sun actually is, or what it does to the space around it. The sun is not simply a ball of fire sitting in the middle of empty space. It is an engine, a furious, continuously exploding engine that pumps an invisible stream of charged particles outward in every direction, at every moment, without stopping. Scientists call this stream the solar wind, and it does not stop at Mercury, it does not stop at Earth, it does not stop at Jupiter or Saturn or Neptune. It keeps going, and going, and going. Long after the last planet disappears behind you, the solar wind is still rushing outward into the dark, at speeds approaching 1 million miles per hour. Now, here is the thing most people do not realize. That solar wind is what defines the solar system. Not the planets, not the asteroids, not the comets. The solar system, in its truest sense, is the enormous bubble of space carved out by the sun's constant outward breath. Everything inside that bubble is, in some meaningful way, touched by our star. Everything inside it exists under the sun's gravitational grip and its magnetic influence. And the outer edge of that bubble, the place where the solar wind finally loses its battle against the pressure of interstellar space. That is where our solar system truly ends. That edge has a name. Scientists call it the heliopause, and for most of human history, we had absolutely no idea what it looked like, where exactly it was, or what we would find if we ever reached it. Think about what that means for a moment. We have mapped the ocean floors. We have charted the deepest trenches on Earth. We have sent probes to every planet in the solar system, landed machines on Mars, and dropped a spacecraft into the atmosphere of Jupiter. And yet the actual boundary of the place we live, the outer wall of our own cosmic home, remained completely unknown to us until just a few decades ago. That is not a small thing. That is the equivalent of living your entire life in a house without ever knowing how big the house was, or what was on the other side of the walls. For most of human history, that was us. We were inside the house, and the walls were invisible. The first serious attempts to understand the outer solar system came in the mid-20th century, when scientists began developing theoretical models of the heliosphere. They knew the solar wind existed, they could measure it near Earth, and they understood, mathematically, that it had to thin out and slow down somewhere far beyond the planets. But the models were exactly that, models, educated guesses, elegant equations that described a place no instrument had ever touched. There was only one way to truly know what was out there. You had to go there. And in the summer of 1977, humanity decided to try. 2 spacecraft were launched within weeks of each other from Cape Canaveral, Florida, Voyager 1 and Voyager 2. They were extraordinary machines for their time, though by modern standards, they were almost absurdly limited. Each spacecraft carried about 68 kilograms of scientific instruments. Their onboard computers had less processing power than the phone in your pocket. Their radio transmitters, the ones that would eventually need to send signals across billions of miles of empty space, operated at 22 watts. To put that in perspective, a standard incandescent light bulb in a bedside lamp uses about the same amount of power. These 2 machines, built with 1970s technology and running on power equivalent to a small lamp, were sent out to find the edge of the solar system. And against all reasonable expectation, they succeeded. But the journey was not quick. It was not a matter of weeks or months or even a few years. Voyager 1 crossed the orbit of Neptune in 1989, 12 years after launch, and even then, it was nowhere near the edge. The solar wind was still strong. The sun's magnetic field was still measurable. There was still an enormous distance left to cover, a distance so vast that even light, travelling at nearly 300,000 kilometers per second, would take hours to cross it. The spacecraft kept going, year after year, decade after decade, sending back faint signals that scientists strained to hear, picking them out from the noise of the universe with the largest radio antennas ever built. And all the while, the instruments on board were watching, measuring, waiting for the moment when everything would change. That moment, when it finally came, was nothing like the clean, dramatic boundary that scientists had imagined. There was no sharp line in space, no sudden wall. Instead, there were layers, strange, turbulent layers of particle chaos and magnetic confusion, each one more disorienting than the last. And woven through the data, hints of things that should not have been there, signals that did not match any prediction, readings that made physicists pause and look at their models again with fresh uncertainty. The edge of the solar system was real. The instruments confirmed it. But what they found along the way, and what they detected the moment they crossed into true interstellar space, opened a set of questions that scientists are still struggling to answer today. That is where we're going tonight. Out to the edge, out to the place where the sun lets go and the darkness of the galaxy takes over. We are going to follow the path those 2 small machines traced across half a century of silent flight. We're going to stand at the heliopause and look both inward and outward. And we're going to sit with what NASA actually found hiding at that boundary. Not the clean, tidy edge that the textbooks described. Something far stranger. Something that changes the way you think about where home ends and the unknown begins. Close your eyes for a moment and picture the solar system. I am willing to guess what you see. You see the sun at the centre, burning bright and orange. You see 8 planets arranged in neat concentric rings around it. Maybe you see the asteroid belt between Mars and Jupiter, a band of rocky debris floating in a tidy circle. You see Saturn with its rings. You see Neptune at the far edge, dark blue and distant. And then beyond Neptune, you probably see nothing. Just empty space. Just the void stretching outward until it meets the stars. That image is the one that most of us carry from school textbooks and science posters and television documentaries. It is recognizable, it is orderly, and it is profoundly, almost embarrassingly, incomplete. The solar system does not end at Neptune, not even close. What lies beyond Neptune is not empty space, but one of the most complex and poorly understood regions in all of astronomy. A vast collection of structures, layered one inside the other, like the skins of an enormous invisible onion. Each layer has its own character, its own physics, its own mysteries. And the outermost layer, the true boundary of the solar system, lies so far beyond Neptune that the distance comparison is almost impossible to hold in your mind. Neptune orbits the Sun at roughly 2.8 billion miles. The heliopause, the actual edge of our solar system, sits somewhere between 11 billion and 13 billion miles from the Sun, depending on the direction you're measuring. That is not a small difference. That is nearly 5 times the distance from the Sun to Neptune, wrapped in structures we are only beginning to understand. Let us start rebuilding that mental image together, slowly, because the real shape of the solar system is something worth sitting with. Imagine you're standing in a vast field at night. At the centre of the field is a bonfire. That bonfire is the Sun. The planets are scattered around it at various distances, some close, some far. But the bonfire is doing something that a normal fire does not do. It is blowing. Continuously, in every direction, it pushes an invisible wind outward, a wind made of charged particles called protons and electrons, travelling at extraordinary speed. That wind does not stop when it passes you. It keeps blowing, pushing past the edge of the field, past the tree line, past everything you can see. It carves out a bubble in whatever surrounds the field. And that bubble, that enormous sphere of solar influence, is the true solar system. Everything inside the bubble belongs to our Sun. Everything outside belongs to something else entirely. The bubble has a technical name, the heliosphere. It is one of the most important concepts in planetary science, and yet most people have never heard of it. The heliosphere is not a physical shell. You could not touch it or see it if you flew through it. It is a region of space defined entirely by the dominance of the solar wind. Inside the heliosphere, the particles streaming from the Sun are more numerous and more energetic than the particles drifting in from the rest of the galaxy. The Sun wins, in other words. Its breath fills the space, but as you move outward, away from the Sun, that breath weakens. The particles thin out, the pressure drops, and eventually you reach a point where the solar wind collides head-on with the interstellar medium, the diffused gas and dust and magnetic fields that fill the space between the stars. That collision point is where everything gets strange. Here is something that genuinely unsettled scientists when the data first came in. The heliosphere is not symmetrical. The textbook image showed it as a smooth, round bubble, perhaps slightly elongated in the direction the Sun moves through the galaxy. But the Voyager spacecraft, travelling in 2 different directions, crossed the first major boundary of the heliosphere at very different distances from the Sun. Voyager 1 crossed it at about 84 astronomical units from the Sun. Voyager 2, travelling in a different direction, crossed it at about 76 astronomical units. That is a difference of roughly 1 billion miles depending on which direction you point. The bubble was not the same size in every direction. Something outside the heliosphere was pushing in unevenly, and that implied that the interstellar medium surrounding our solar system was not the smooth, featureless void that early models assumed. Before we go further, it is worth pausing to let the scale settle in. An astronomical unit is the distance from the Earth to the Sun, roughly 93 million miles. Voyager 1 crossed that first boundary at 84 astronomical units. That means it had travelled 84 times the distance from the Earth to the Sun before it even reached the inner layers of the heliosphere boundary. And the true edge, the heliopause, was still billions of miles further out. When Voyager 1 finally crossed the heliopause in 2012, it was at about 121 astronomical units from the Sun. 121 times the Earth-Sun distance. The light from the Sun takes about 8 minutes to reach Earth. At that point in Voyager's journey, a signal travelling at the speed of light took more than 16 hours to reach the spacecraft. These are not numbers that fit easily in the human mind. They are not supposed to. They are the measurements of a place that exists entirely outside the scale of anything your body has ever experienced. And yet here is the thing that I find most remarkable about all of this. Even at that extraordinary distance, Voyager 1 was still inside the solar system by some definitions. Because beyond the heliopause lies the Oort cloud, a vast spherical shell of icy bodies that may extend nearly 1/4 of the way to the nearest star. The Sun's gravity reaches that far. In that sense, the solar system stretches almost incomprehensibly further than even the heliosphere suggests. We are not just residents of a small rocky planet orbiting an average star. We are residents of a cosmic structure so large that it would take a spacecraft travelling faster than any object humans have ever built, thousands of years to cross from one side to the other. This is the solar system you actually live in. Not the tidy diagram on the classroom wall, not the neat rings of coloured planets arranged in order of size. The real solar system is a dynamic, layered, asymmetric bubble of solar influence, surrounded by a churning interstellar medium, wrapped in a shell of ancient ice, and embedded in a galaxy that is actively pressing in from every side. It is messy, it is enormous, it is only partially mapped, and the more closely scientists look at the boundary between our bubble and the universe beyond it, the more they find things that do not fit the models. Things that suggest the edge of our solar system is not a passive boundary, but an active, complicated interface between two very different regions of space. That interface is where our journey is headed, and what is waiting there, quietly, in the data NASA has collected over 50 years of deep space exploration, is something that should fundamentally change the way you think about home. On the 5th of September 1977, a rocket lifted off from Cape Canaveral, Florida, and began carrying a small golden machine away from the Earth. The machine was called Voyager 1. It was not the first spacecraft humanity had sent into the outer solar system, but it would become the most important. Nobody watching that launch, not the engineers, not the scientists, not the journalists gathered at the fence line, could have fully understood what they were witnessing. They were not just watching a spacecraft launch. They were watching the beginning of the longest journey any human-made object would ever take. A journey that is still ongoing today, nearly 5 decades later, and will continue long after every person alive on Earth right now has died. The Voyager spacecraft were products of a very particular moment in American science. The 1970s were a time of extraordinary ambition in space exploration. NASA had just completed the Apollo program, had put 12 human beings on the surface of the Moon, and was looking for its next great challenge. A small group of scientists and engineers, led in part by the legendary planetary scientist Carl Sagan, recognized that a rare alignment of the outer planets was approaching. Once every 175 years, Jupiter, Saturn, Uranus, and Neptune arrange themselves in a configuration that allows a single spacecraft to visit all 4 using a technique called gravity assist, essentially using each planet's gravitational pull as a slingshot to redirect and accelerate toward the next. The window for this alignment would open in the late 1970s and close quickly. If NASA did not launch before 1977, the next opportunity would not come until the 22nd century. The decision was made. 2 spacecraft would be built and launched within weeks of each other. They would be called Voyager 1 and Voyager 2. The spacecraft themselves were remarkable for their time, though by modern standards, they seem almost impossibly primitive. Each Voyager weighed about 825 kilograms at launch. They were equipped with a suite of scientific instruments designed to measure magnetic fields, plasma, charged particles, infrared radiation, and ultraviolet light. They carried cameras, they carried radio receivers, and mounted to the body of each spacecraft was a large parabolic dish antenna, 3.7 meters across, pointed permanently back toward Earth to relay their findings home. The onboard computers that managed all of this had a combined memory of about 68 kilobytes. A single low-resolution photograph on your phone contains more data than the entire memory of the computers guiding Voyager across interstellar space. The thought is both humbling and extraordinary. Voyager 2 launched first on the 20th of August, 1977. Voyager 1 followed 16 days later on the 5th of September. Despite launching second, Voyager 1 was placed on a faster, more direct trajectory and quickly overtook its twin. Both spacecraft executed their planetary tours brilliantly. Voyager 1 flew past Jupiter in March of 1979, revealing volcanic eruptions on the moon Io that no one had predicted, discovering a thin ring around the planet and capturing images so detailed and so beautiful that scientists wept when they saw them. It reached Saturn in November of 1980, where it made a close flyby of the moon Titan, discovering a thick nitrogen atmosphere that reminded researchers of early Earth. That Titan flyby set Voyager 1 on its current trajectory, angled upward out of the plane of the solar system and aimed toward the edge of the heliosphere. From that moment on, there would be no more planetary flybys, just the long, dark, silent journey outward. Voyager 2 took a different path. It visited Jupiter and Saturn as well, but then continued on to Uranus in January of 1986 and Neptune in August of 1989. That Neptune flyby remains, to this day, the only close observation of that distant blue world humanity has ever achieved. After Neptune, Voyager 2 was also released into the long dark, aimed in a different direction from its twin, angled downward out of the solar plane. 2 probes, 2 directions, both heading for the same invisible boundary, both carrying the same question into the same darkness. What is out there at the edge of everything we know? Power has always been the critical constraint on both missions. The Voyagers do not run on solar panels because at the distances they travel, sunlight is far too faint to be useful. Instead, they are powered by radioisotope thermoelectric generators, devices that convert the heat produced by the natural decay of plutonium-238 into electricity. At launch, each generator produced about 470 watts of power. But radioactive decay is relentless and slow, and over the decades the power output has dropped steadily. By the early 2020s, each spacecraft was producing somewhere around 250 to 300 watts, barely enough to run a few instruments and keep the heater systems from failing entirely. NASA engineers have been making increasingly difficult choices about which instruments to keep on and which to shut down, essentially performing triage on machines that are more than 1 billion miles away and cannot be physically serviced. Every watt matters. Every degree of warmth matters. Because the moment a critical system freezes or the power drops below a minimum threshold, the signal will go silent and the most distant human-made objects in existence will become unreachable forever. The communication link between the Voyagers and Earth is itself one of the most astonishing engineering achievements in history. The signal from Voyager 1, traveling at the speed of light, takes more than 22 hours to reach Earth today. By the time you receive a response to any command you send, nearly 2 days have passed. The signal itself, when it finally arrives, is extraordinarily faint. Scientists describe it as arriving at a power level of about 10 to the minus 16 watts. That is 0.00000000000000000001 watts. To detect something that faint requires the largest radio antennas on the planet, the dishes of NASA's Deep Space Network, some of which stretch 70 meters across, working in concert with the most sensitive receivers ever built. The fact that we can still hear these machines, still understand what they're telling us, from a distance of more than 22 billion miles, is not just impressive, it is borderline miraculous. And what Voyager 1 and Voyager 2 have been telling us as they crept outward decade by decade toward the edge of the solar system has repeatedly surprised the people listening. They did not find what the models predicted. They found something more complicated, more layered, and in some ways more unsettling. They found a boundary that behaved differently depending on which direction you approached it. They found particles and magnetic fields doing things that existing theories could not fully explain. And when Voyager 1 finally crossed into interstellar space in 2012, the data it sent back in the hours and days following that crossing quietly rewrote entire chapters of heliospheric physics. Two small machines, built in the 1970s running on power barely sufficient to keep a lamp lit, have taught us more about the true edge of our solar system than all the telescopes and theoretical models of the preceding century combined. What they found there is what we're going to spend the rest of tonight exploring together. Imagine standing at the edge of a very powerful waterfall. The water rushes past you at extraordinary speed, white and churning and loud, moving in one direction with absolute certainty. Everything in its path is swept along. There is no negotiating with it. There is no slowing it down. It simply moves fast and relentless, and the world downstream has no choice but to receive it. Now imagine that further downstream, something pushes back. Another force equally vast presses in from the opposite direction, and at some point in the middle, where the two forces meet head-on, the water slows. It piles up. It becomes turbulent and confused, no longer fast and certain but churning and chaotic, energy converting into heat and pressure rather than forward motion. That collision point, that place where the unstoppable flow meets the immovable resistance, is what physicists call a shockwave. And in the outer solar system, there is a shockwave so large that it wraps entirely around our sun. It is called the termination shock, and it is the first sign as you travel outward from Earth that the sun is beginning to lose its grip on the universe around it. The solar wind, as we have established, streams outward from the sun in every direction at roughly 400 kilometers per second on average, though it varies considerably depending on solar activity. At that speed, the solar wind is supersonic, meaning it travels faster than the speed at which pressure waves can propagate through it. This matters enormously in physics because supersonic flows behave very differently from subsonic ones. A supersonic flow cannot be gradually slowed down by the pressure building ahead of it. It cannot receive warning, so to speak, that something is pushing back from the front. The information about the pressure ahead cannot travel fast enough upstream to reach the oncoming solar wind before the wind itself arrives. So instead of a gradual deceleration, you get an abrupt one, a wall of sudden compression, a shock. The termination shock is not a physical object. You could fly through it without feeling anything at all, at least not with your body. It is a region of space, typically estimated to be somewhere between 80 and 100 astronomical units from the Sun, where the solar wind abruptly drops from supersonic to subsonic speeds. In crossing that invisible boundary, the solar wind does not disappear. It simply slows dramatically and heats up. The particles compress. The magnetic field intensifies. The kinetic energy of the wind converts into thermal energy in a sudden, violent reorganization of particle behavior that stretches across an enormous volume of space. On the scale of the outer solar system, the termination shock is not a thin line, but a broad, rippling, constantly shifting boundary that expands and contracts with the rhythm of the Sun's own activity cycle. Voyager 1 crossed the termination shock in December of 2004 at approximately 84 astronomical units from the Sun. Scientists had been anticipating the crossing for years, watching the particle and magnetic field data for signs that the boundary was approaching, and when it came, the signatures were unmistakable. The low-energy charged particle count spiked dramatically. The magnetic field strength increased. The behavior of the plasma surrounding the spacecraft shifted in ways that matched the theoretical predictions of what a shock crossing should look like. The team at the Jet Propulsion Laboratory in Pasadena confirmed the crossing after careful analysis of the data, and the announcement was quiet but significant. Humanity had detected the first boundary of the edge of the solar system. Voyager 1 had passed through the outer wall of the supersonic solar wind. It was, in every meaningful scientific sense, a historic moment, but here is where things started to get genuinely interesting and a little unsettling. Voyager 2 crossed the termination shock in August of 2007, nearly 3 years after its twin, and it crossed at only about 76 astronomical units from the Sun. That is roughly 8 astronomical units closer to the Sun than where Voyager 1 had crossed, a difference of nearly 750 million miles. The two spacecraft were travelling in different directions, one angled above the solar plane and one below it, so scientists had expected some difference in the crossing distance. The heliosphere was not expected to be a perfect sphere, but the difference they found was larger than the models had comfortably predicted. 8 astronomical units is not a minor variation. It is a significant asymmetry, and it pointed to something pressing in on the heliosphere more forcefully from one side than the other. Something in the interstellar medium surrounding our solar system was not uniform. It was not smooth. It was uneven, directional, structured in ways that the early models had not fully accounted for. Voyager 2's crossing of the termination shock was in some ways even more scientifically valuable than Voyager 1's, because Voyager 2 carried a working plasma science instrument that Voyager 1 had lost years earlier. That instrument allowed scientists to make direct measurements of the plasma in the heliosheath, the region just beyond the termination shock, with a level of detail and confidence that Voyager 1's data alone could not provide. What they found was that the solar wind in the heliosheath was not simply slow and hot, as the basic models predicted. It was also unexpectedly thin. There were fewer particles than expected. The energy balance did not add up in the way the equations said it should. Somewhere in the crossing, particles were escaping the model's accounting. Energy was going somewhere that the instruments were not catching. The termination shock was real, confirmed by 2 independent spacecraft from 2 different directions. But what was happening inside it, and immediately beyond it, was messier than anyone had prepared for. What this asymmetry and these energy discrepancies told scientists was something genuinely profound. The boundary of our solar system is not a static structure. It breathes, it shifts, it responds dynamically to the pressure of the interstellar environment pushing in from outside. When the Sun is more active, during the peak of its 11-year sunspot cycle, it blows a stronger solar wind, and the heliosphere expands outward, pushing the termination shock further from the Sun. When the Sun is quieter, the heliosphere contracts slightly, and the termination shock drifts inward. The boundary of our solar system is alive in this sense, always moving, always negotiating its position with the cosmos beyond it. That is not the image of a fixed wall separating the known from the unknown. It is something far more dynamic, far more interesting and far harder to pin down with simple equations. The termination shock is, in the end, a kind of threshold. It is the first announcement that you are approaching the true edge. Beyond it, the solar wind no longer rushes with confidence. It stumbles, it churns, it fills a vast, turbulent region called the Helios Heath, before eventually reaching the final boundary, where the sun's influence ends entirely. Crossing the termination shock does not mean you have left the solar system, not even close. It means you have entered the outermost atmosphere of our star's reach, a place where the laws of solar physics and the laws of interstellar space conduct a long, complicated negotiation. It is a place of compression and heat and magnetic confusion. It is a place where the certainty of the inner solar system gives way to something far less predictable, and it is where the truly strange discoveries were waiting. Think about the ocean on a stormy night. Not the surface with its waves and spray and visible chaos, but the deep interior, where the currents move in directions that have nothing to do with the wind above, where warm water collides with cold, where pressure builds and releases in slow, enormous cycles invisible to anyone standing on the shore. The ocean in that moment is not calm. It is not empty. It is a dynamic, turbulent system full of energy and motion and complexity that would take a lifetime to fully map. Now scale that image up to something almost impossibly larger. Stretch it across billions of miles. Fill it not with water, but with charged particles, magnetic fields, and the slowing remnants of a stellar wind that has been blowing for 4.5 billion years. What you have is the Helios Sheath, the strange, churning, poorly understood region that lies between the termination shock and the true edge of the solar system. It is one of the most complex environments in the known universe, and until the Voyager spacecraft passed through it, we had almost no direct data about what it contained. The Helios Sheath begins at the termination shock, that invisible boundary where the solar wind drops from supersonic to subsonic speeds and extends outward to the heliopause, the final frontier where the sun's influence ends entirely. In the direction Voyager 1 was travelling, that meant the Helios Sheath was roughly 37 astronomical units thick, 37 times the distance from the Earth to the Sun, a region of space so vast that light takes more than 5 hours to cross it, and yet it is just one layer in the larger structure of the outer solar system. Inside that enormous volume, the decelerated solar wind does not simply stop and wait. It fills the space like a slow pressurized fluid, compressed by the interstellar medium pushing in from outside, heated by the energy released at the termination shock, and twisted by magnetic forces that behave very differently here than they do anywhere closer to the Sun. One of the first things Voyager 1 detected after crossing the termination shock was deeply puzzling. The models that scientists had spent decades developing predicted that the solar wind, once slowed to subsonic speeds, should continue moving generally outward and eventually pile up near the heliopause before being deflected around the sides of the heliosphere. It should behave, in other words, a bit like water flowing around the front of a boat, pressing forward and then curving away to the sides. But the plasma data from Voyager 1 told a different story. The outward flow of the solar wind in the Helios Sheath was far weaker than expected. In some measurements, scientists could barely detect it at all. The decelerated solar wind was not neatly flowing outward. It appeared to be doing something more complicated, moving in unexpected directions, mixing with particles coming from outside, behaving more like a turbulent eddy than a smoothly redirected stream. The models were not wrong in outline, but they were significantly wrong in the details. Voyager 2's plasma instrument, which remained functional throughout its Helios Sheath transit in ways that Voyager 1's had not, added crucial texture to this picture. As Voyager 2 moved through the Helios Sheath between 2007 and 2018, its plasma science team detected multiple, unexpected changes in the speed and direction of the solar wind plasma. There were layers within the Helios Sheath where the flow changed abruptly, where the magnetic field strength jumped or shifted direction without obvious cause, where the temperature of the plasma spiked suddenly before dropping again. The heliosheath was not a uniform zone of slow, hot, compressed solar wind. It was layered. It was variable. It was, in the truest sense of the word, turbulent. Not in a way that was random and featureless, but in a way that suggested complex, structured behavior driven by forces that the instruments were only partially equipped to measure. Among the most significant findings from the heliosheath was the behavior of energetic neutral atoms, a type of particle created when fast-moving charged particles from the interstellar medium collide with slow-moving ions in the heliosheath and exchange charges, producing neutral particles that can travel in straight lines, unaffected by magnetic fields. These particles were being detected not just by the Voyager spacecraft, but also by a separate NASA mission called IBEX, the Interstellar Boundary Explorer, which had been launched in 2008 specifically to map the heliosphere's boundaries from Earth orbit by detecting these energetic neutral atoms as they streamed inward. What IBEX saw and what the Voyager data confirmed was that the heliosheath was producing these particles in enormous quantities, far more than the models predicted, and that they were not distributed evenly. They were concentrated in certain regions and absent in others, a patchwork of particle density that implied the heliosheath was not a simple buffer zone, but an active, complex interface between two very different physical regimes. There is something almost meditative about the heliosheath when you sit with it long enough. It is a place that has existed since the solar system formed. For 4.5 billion years, the solar wind has been blowing outward, slowing at the termination shock, filling this vast region with heated, compressed plasma, pressing against the boundary of the interstellar medium. Long before the Earth existed, the heliosheath was there. Long before the first single-celled organisms appeared in the ancient oceans, this enormous churning zone of charged particles was doing exactly what it does now, mediating the boundary between our Sun's kingdom and the wider galaxy. And we only sent the first instrument capable of detecting it directly in 1977. We only received its measurements for about a decade of the transit through that zone. In cosmic terms, our dataset is the equivalent of dipping a finger into the ocean for a fraction of a second and calling it a survey. What makes the heliosheath particularly important and particularly humbling is its role as a filter. The galactic cosmic rays that stream through interstellar space are extraordinarily energetic, far more energetic than anything the Sun routinely produces. If they reached the inner solar system in their full intensity, they would pose a serious radiation hazard to life on Earth and to any future human travelers in deep space. The heliosheath, combined with the termination shock and the heliopause, acts as a series of barriers that slow, deflect, and absorb much of this galactic radiation before it can reach us. The heliosheath is not just a scientific curiosity, it is part of the protective system that makes complex life on Earth possible. And the more we learn about how turbulent and variable it is, the more we appreciate how dynamic that protection actually is. Not a fixed shield, but a constantly shifting one, breathing with the Sun's activity cycle, pressing outward and contracting inward, always negotiating with the cosmos on our behalf. Beyond the heliosheath, just a little further out in the dark, lies the final boundary, the place where the Sun's influence ends completely and the true interstellar medium takes over. The Voyager spacecraft spent years crossing the heliosheath, sending back data that rewrote textbooks and raised new questions faster than the old ones could be answered. And when they finally reached that last boundary and crossed it, what they detected in those first moments on the other side was something that no model, no equation, and no telescope had fully prepared scientists to receive. There are moments in exploration that change everything. Not just the data, not just the models, not just the textbooks, but something deeper and harder to name. The feeling that the world has shifted slightly on its axis, that something that was abstract has become real, that a boundary which existed only in equations has suddenly been confirmed as a place, a genuine location in space with measurable coordinates and detectable properties. August of 2012 was one of those moments. After 35 years of travelling through the solar system and across the heliosheath, Voyager 1 crossed the heliopause, the outermost boundary of our Sun's kingdom, and became the first human-made object in history to enter interstellar space. For the scientists tracking its journey from Earth, it was the culmination of careers spent listening to a faint signal from an impossibly distant machine. For the rest of us, it should have been a moment of profound collective wonder. The species that evolved on a small rocky planet had reached the edge of its home star's influence and touched for the first time the space between the stars. The heliopause is the boundary where the outward pressure of the solar wind exactly balances the inward pressure of the interstellar medium. On one side, the Sun's charged particles dominate the environment. On the other side, the particles and magnetic fields of the interstellar medium take over completely. It is not a physical wall. It is not a line you could draw on a map with perfect precision. It is a dynamic pressure equilibrium, a place defined entirely by the balance of two competing forces, and it shifts position constantly as both the solar wind and the interstellar medium fluctuate. But it is real, and when Voyager 1 crossed it, the instruments knew immediately. The data that came back across 22 hours of radio travel time told a story that was clear, dramatic, and in some details deeply surprising. The most definitive measurement came from the plasma wave instrument aboard Voyager 1. In April of 2013, scientists used this instrument to measure the density of the plasma surrounding the spacecraft, and the number they got back was 40 times higher than what they had measured inside the heliosphere. 40 times! That single measurement confirmed beyond any reasonable doubt that Voyager 1 had left the solar wind environment and entered the interstellar medium, where the plasma is far denser and far colder than what fills the heliosheath. The spacecraft had crossed the heliopause sometime in August of 2012 at a distance of approximately 121 astronomical units from the Sun. More than 11 billion miles from home. The confirmation took months because the evidence had to be assembled carefully from multiple instrument readings, each one providing a different piece of the same picture. But when it came, the conclusion was unambiguous. Voyager 1 was in interstellar space. What surprised scientists most about the crossing was not the plasma density jump, which was expected in general terms, but the behavior of the magnetic field. The models had predicted that when Voyager 1 crossed the heliopause, the direction of the magnetic field should change dramatically. Inside the heliosphere, the magnetic field is generated by the Sun and follows the Sun's rotational structure, spiraling outward in what is called the Parker spiral, named after the physicist Eugene Parker, who first described it in the 1950s. The interstellar magnetic field, by contrast, was expected to run in a completely different direction, oriented by the large-scale structure of the galaxy rather than by our star. Scientists anticipated a clear, sharp rotation in the field direction at the crossing point. What they found instead was that the magnetic field direction did not change significantly. The field outside the heliopause was aligned much more closely with the field inside than the models had predicted. This was not a minor discrepancy. It suggested that the interstellar magnetic field in our immediate neighbourhood is oriented in a way that is somehow coupled to, or at least closely aligned with, the Sun's own magnetic influence. Why that is the case remains one of the genuinely open questions in heliospheric physics today. Voyager 2 crossed the heliopause in November of 2018 at a distance of about 119 astronomical units from the Sun, slightly closer than where Voyager 1 had crossed, and in a different direction below the solar plane. This second crossing was enormously valuable precisely because Voyager 2 carried a functioning plasma science instrument, giving scientists their first direct measurements of the plasma conditions on both sides of the heliopause simultaneously, in a way that Voyager 1's data alone had not allowed. What Voyager 2's plasma instrument revealed at the moment of crossing was striking. The boundary itself was extraordinarily thin. The transition from heliospheric plasma to interstellar plasma appeared to happen over a region less than a single astronomical unit wide. For a boundary that had taken decades to reach and that separates two fundamentally different physical environments, a transition zone less than 93 million miles wide is remarkably sharp. The heliopause is not a gradual fade. It is, by cosmic standards, a knife edge. Voyager 2 also detected something unexpected at the crossing point itself. There was a thin layer of heated plasma just inside the heliopause, a region where the temperature spiked dramatically before dropping to interstellar values on the other side. Scientists interpreted this as a region where solar wind plasma had piled up against the inner face of the heliopause, compressed and heated by the pressure from the interstellar medium pushing in from outside. The existence of this thin, hot layer had been theorized, but seeing it confirmed in direct measurements added an important new detail to the picture of what the heliopause actually looks like up close. It is not simply a contact surface between two regions of equal pressure. It is a dynamic, compressed boundary with its own internal structure, a thin seam of extraordinary heat sandwiched between the cooling heliosheath and the cold interstellar medium beyond. Beyond the heliopause in the first measurements from true interstellar space, both Voyager spacecraft found a universe that was quieter in some ways and stranger in others. The cosmic ray intensity increased sharply, confirming that the heliosphere had been shielding the inner solar system from a significant fraction of galactic radiation. The temperature of the plasma dropped. The magnetic field stabilized into a more uniform orientation. But the interstellar medium was not the featureless void that older models had assumed. There were variations in density, fluctuations in the magnetic field, hints of structure and turbulence that suggested the space immediately surrounding our solar system had its own complex character. The solar system does not sit in an empty corner of the galaxy. It sits inside a specific region of interstellar space with its own history, its own physical properties, and its own surprises waiting to be discovered. For me, there is something quietly terrifying and quietly beautiful about the heliopause. It is the membrane that separates home from everything else. Everything you have ever known, every human being who has ever lived, every civilization, every war, every act of love and cruelty and creation in the entire history of our species, all of it happened inside this bubble. On one side of that invisible boundary, the sun is still in charge, still filling space with its particles and its light and its magnetic personality. On the other side, it is just another star, a faint point of light among hundreds of billions of others, indistinguishable to any observer who did not already know where to look. Voyager 1 crossed that boundary. It went to the other side, and it is still out there now, in the dark between the stars, sending back whispers of data that scientists strain to hear, telling us, in the quiet language of particle counts and magnetic field measurements, what it is like to be beyond the edge of everything we have ever called home. Science moves in two directions at once. It moves forward through confirmation, through the satisfaction of finding exactly what the equations predicted, through the slow accumulation of evidence that builds a model into certainty. But it also moves forward through contradiction, through the moment when an instrument returns a reading that makes a physicist stop, look at the number again, check the calibration, check it a second time, and then sit back in their chair with a feeling that is equal parts excitement and unease. That second kind of movement is often where the most important discoveries live. And as the Voyager spacecraft moved through the heliosheath and eventually crossed the heliopause, they generated that second kind of moment repeatedly. Not once, not twice, but across years of data, in multiple instrument channels, in readings that should have matched the models and quietly, persistently, did not. Let us start with the particles. The inner heliosphere, the region of space from the Sun out to the termination shock, is filled with solar energetic particles, charged particles, accelerated to high speeds by solar flares and coronal mass ejections from the Sun. These particles are well understood. Scientists can predict their behavior, their energy distributions, their density gradients, but the termination shock is also a particle accelerator of its own kind. The theory predicted that when the solar wind slammed into the termination shock and decelerated abruptly, some fraction of the particles would be reflected and accelerated to very high energies, becoming what scientists call anomalous cosmic rays. These anomalous cosmic rays were expected to peak in intensity near the termination shock, and then thin out as you moved further into the heliosheath. What Voyager 1 found was significantly different. The anomalous cosmic rays did not peak at the termination shock. They continued to increase as Voyager moved through the heliosheath, and then, at the heliopause, they essentially vanished. Completely. The particles that were supposed to be products of the termination shock were somehow being accelerated, not at the shock, but somewhere else, possibly at the heliopause itself, or in the heliosheath between them. Where exactly and how exactly remained deeply unclear. Then there was the issue of the magnetic field. As we discussed in the previous chapter, the magnetic field direction did not rotate as dramatically as expected at the heliopause crossing. But the anomalies in the magnetic field data began much earlier, deep inside the heliosheath, long before Voyager 1 reached the final boundary. Scientists tracking the magnetic field data noticed that it was not behaving like a simple extension of the Sun's Parker spiral. There were kinks, there were reversals, regions where the field direction flipped unexpectedly and then flipped back. The heliosheath magnetic field was tangled in ways that suggested something was pressing in from the outside and distorting the field from within. The interstellar medium was not passively waiting at the heliopause. It was somehow reaching inside, influencing the magnetic structure of the heliosheath in ways that the models had not predicted. This was not supposed to happen. The heliopause was supposed to be a clean boundary, but the data suggested it was leaking. The plasma data added another layer of confusion. In 2012, in the months leading up to and following the heliopause crossing, Voyager 1 detected something that scientists have described as one of the most puzzling readings in the mission's history. The spacecraft entered a region that some researchers initially called the magnetic highway, a zone where the magnetic field was unusually smooth and well organized, running at an angle that allowed solar energetic particles to escape outward along the field lines, while interstellar particles streamed inward along the same lines. Particles were moving in both directions simultaneously along these organized magnetic channels, inward from the interstellar medium and outward from the heliosphere, passing through the boundary as if it were partially transparent. The heliopause was acting less like a sealed container and more like a semi-permeable membrane. Materials were crossing it in both directions. The clean separation between inside and outside that the textbooks described was not what the instruments were actually measuring. In the years following the heliopause crossing, Voyager 1 continued to return data from interstellar space, and those readings raised new questions of their own. In 2014 and again in 2015, the plasma wave instrument on Voyager 1 detected oscillations in the density of the interstellar plasma surrounding the spacecraft. These oscillations were caused by solar events back home. When the Sun produced a particularly powerful coronal mass ejection, a massive eruption of plasma and magnetic field that sent a pressure wave outward through the solar wind. That wave eventually reached the heliopause, crossed it, and continued into the interstellar medium, producing detectable ripples in the plasma density around Voyager 1. Scientists used these ripples to measure the density of the local interstellar medium with a precision that had never before been possible. But the deeper implication was striking. Events on the surface of the Sun were producing detectable effects in the interstellar medium more than 11 billion miles away. The Sun's influence did not simply end at the heliopause, it propagated across it, sent ripples into the space beyond it, and left measurable signatures in a region that was supposed to be entirely beyond its reach. Voyager 2's crossing in 2018 added one more piece to this complicated puzzle. When Voyager 2 crossed the heliopause, its plasma instrument detected a thin layer on the outer edge of the boundary where the interstellar plasma was measurably hotter than it should have been. Not dramatically hotter, not hot by any human standard, but statistically, detectably hotter than the surrounding interstellar medium in a way that suggested the boundary region itself was generating heat through the friction and compression of the two colliding environments. The heliopause was not a passive surface, it was an active site of energy exchange, particle mixing, and physical processes that were still operating in ways that the models could describe only partially. And on the interstellar side of that boundary, the plasma density and temperature measurements did not match the values that astronomers had estimated for the local interstellar medium from distant observations. The neighbourhood just outside our solar system was different in measurable ways from what the telescope data had suggested. The environment immediately surrounding the heliopause had its own distinct character that only a spacecraft passing through it could reveal. Taken together, these anomalies paint a picture of the heliospheric boundary that is far more complex and far more dynamic than the textbooks of the 1980s and 90s described. The termination shock accelerates particles in unexpected ways. The heliosheath is magnetically tangled and turbulent in ways the models underestimated. The heliopause leaks, allowing particles and pressure waves to pass through in both directions. And the interstellar medium just beyond it is structured and variable in ways that distant observations alone could not have revealed. Each anomaly on its own might be explainable as a modelling error, a local fluctuation, an instrument artifact. But taken together, across two spacecraft, across decades of data, across multiple independent instrument channels, they suggest something more fundamental. The boundary of our solar system is not a simple edge. It is a complicated, active, partially understood interface between our star and the galaxy. And embedded in those anomalies, quietly waiting for someone to piece together the right explanation, is a discovery that would prove to be among the most startling in the entire history of heliospheric science. Something that no model had predicted, something that only a completely different kind of instrument, looking at the boundary from the inside out rather than from the outside in, would finally reveal. In October of 2009, NASA held a press conference that drew relatively little mainstream attention, but sent a quiet shockwave through the community of scientists who study the outer solar system. The announcement concerned a new spacecraft called IBEX, the Interstellar Boundary Explorer, which had been launched just 1 year earlier in October of 2008. IBEX was a small satellite about the size of a bus tire placed in a high Earth orbit, specifically designed to map the heliosphere's boundary from the inside. It did not travel to the edge of the solar system. It did not need to. Instead, it detected energetic neutral atoms, those particles produced when fast interstellar ions collide with slow heliospheric ions and exchange an electron, becoming neutral and flying inward in straight lines unaffected by magnetic fields. By detecting these particles from Earth orbit and tracing them back to their points of origin, IBEX could build a map of the entire heliospheric boundary, the way a camera builds an image, one particle at a time. What that map showed, in the very first full-sky image IBEX produced, was something that left the science team in a state of stunned disbelief. Stretched across the sky, arcing from one side of the heliosphere to the other, was a bright, narrow ribbon of energetic neutral atom emission that no one had predicted, no model had suggested, and no existing theory could immediately explain. The ribbon was not a subtle feature. It was not something that required careful statistical analysis to detect or that could be dismissed as instrumental noise. It was bright. It was narrow, spanning roughly 20 degrees of arc in width, but extending across a huge fraction of the full sky map. It was 2 to 3 times brighter than everything around it. When the IBEX team released the image, one of the lead scientists described the reaction in the room as something close to shock. The models that had guided heliospheric research for decades, the models that had predicted the general shape and structure of the heliosphere with reasonable accuracy, had not produced anything resembling this ribbon. Nothing in the theoretical framework that existed in October of 2009 said there should be a bright arc of energetic neutral atoms wrapping around the heliosphere like a luminous seam on a cosmic baseball. And yet there it was, measured, confirmed, utterly unexpected. The geometry of the ribbon offered the first clue to its possible origin. When scientists examined the IBEX map carefully, they noticed that the ribbon appeared to trace a path across the sky that was approximately perpendicular to the direction of the local interstellar magnetic field, the large-scale magnetic field of the interstellar medium that surrounds the heliosphere. This was not a coincidence. The alignment was too consistent, too precise to be accidental. Whatever was producing the ribbon, the local interstellar magnetic field, was clearly involved in shaping it. The ribbon appeared to mark the locations on the heliosphere's surface where the interstellar magnetic field lines were tangent to the heliopause, essentially the circle of points where the external magnetic field just grazes the outer boundary of the solar system rather than running into it head-on. That geometric relationship became the starting point for every theoretical explanation that followed. But agreeing on the geometry was the easy part. Agreeing on the physical mechanism responsible for producing that bright ribbon of particles has proved far more difficult. The leading explanation, favoured by many but not all heliospheric physicists, is called the retention theory. In this model, neutral hydrogen atoms from the inner heliosphere stream outward, cross the heliopause and enter the interstellar medium. Once outside, some of these neutral atoms are ionized by ultraviolet radiation from the sun or by charge exchange with interstellar ions, becoming charged particles. As charged particles, they are immediately captured by the local interstellar magnetic field and begin gyrating around the field lines. If they happen to be ionized in the right location, specifically where the interstellar magnetic field is tangent to the heliopause, their circular gyration paths bring them back around to the heliopause, where they can undergo another charge exchange, become neutral again, and fly inward across the heliosphere to be detected by IBEX. The ribbon in this model is essentially a projection of the geometry of the local interstellar magnetic field onto the surface of the heliosphere, revealed by particles that have been cycled out across the boundary and then returned. It is an extraordinarily elegant idea, and it fits the geometry, but the numbers have proven difficult to make work precisely, and some predictions of the retention model do not perfectly match what IBEX has continued to observe across more than a decade of operation. Other explanations have been proposed. One alternative suggests that the ribbon is produced by turbulence in the interstellar magnetic field just outside the heliopause, a region of disturbed and compressed field lines that preferentially emit energetic neutral atoms in the directions that IBEX detects. Another model proposes that the ribbon marks the location of a previously unknown structure in the local interstellar medium, a dense filament or sheet of material that happens to wrap around the solar system in exactly the orientation the IBEX map reveals. Each of these alternatives has supporters and critics. Each can explain some features of the ribbon but struggles with others. The honest scientific assessment, more than 15 years after the initial discovery, is that the ribbon is real. Its connection to the local interstellar magnetic field is established, and its precise physical origin remains genuinely unresolved. No single explanation has yet won the consensus of the field. What makes the ribbon particularly fascinating from a broader perspective is what it tells us about the relationship between the heliosphere and the interstellar environment around it. The ribbon is not just a curiosity, it is a diagnostic. The fact that it exists and that its shape encodes information about the direction and strength of the local interstellar magnetic field means that IBEX has given scientists a new tool for studying the space surrounding the solar system without ever leaving Earth orbit. By tracking how the ribbon's brightness and shape change over time as the heliosphere expands and contracts with the solar activity cycle, scientists can probe the properties of the interstellar medium in ways that were simply not possible before 2008. The ribbon is a window. Narrow and bright, stretched across the sky, it lets us see the environment just outside our solar system more clearly than any previous instrument allowed. But I want to stay with the deeper implication for a moment, because I think it deserves to be felt rather than just noted. Before IBEX, we thought we had a reasonably good model of the heliosphere. We had the Voyager data. We had decades of theoretical work. We had a picture that was incomplete in its details but sound in its broad outlines. And then a satellite the size of a bus tyre spent 1 year making its first full sky map, and it found something so unexpected, so structurally significant, so completely absent from every prior model, that it forced the entire field to pause and reconsider. The universe had hidden an enormous, luminous ribbon of particles wrapping around our solar system in plain sight, and we had simply lacked the instrument to see it. That should make you wonder, as it makes me wonder, what else is out there encircling us, waiting to be revealed by an instrument we have not yet thought to build. The ribbon was not the last surprise waiting at the edge of our solar system. It was not even close to the last. Because when scientists looked at the shape of the heliosphere itself, really looked at it with the new data that IBEX and the Voyager spacecraft had provided, what they found challenged something even more fundamental than a missing ribbon. It challenged the basic shape of the bubble we live inside. If you've ever seen a diagram of the solar system in a science textbook from the 1980s or 90s, there is a good chance it included a small illustration of the heliosphere. It would have shown a teardrop, a rounded bulge on the side facing the direction the sun moves through the galaxy, and a long trailing tail stretching out behind it in the opposite direction, like the wake of a boat moving through water. This image made intuitive sense. The sun is moving through the interstellar medium at about 43,000 miles per hour relative to the surrounding stars. Common sense suggested that the interstellar medium would pile up in front of the heliosphere as the solar system plows through it, compressing the boundary on the leading side, and that the solar wind would be swept back into a long tail on the trailing side, the way a comet's tail always points away from the sun. The teardrop heliosphere. It was elegant, it was intuitive, it appeared in countless educational materials for decades, and the data that has accumulated since the 2000s suggests it is almost certainly wrong. The challenge to the teardrop model began with the Voyager data, but accelerated dramatically after IBEX started returning its full sky maps. If the heliosphere had a long trailing tail, the energetic neutral atom maps that IBEX produced should have shown a clear asymmetry, with the anti-nose direction, the side pointing away from the sun's direction of travel, appearing distinctly different from the sides. The maps showed some asymmetry, but they did not show the dramatic elongated structure that a long comet-like tail would produce. The heliosphere, based on the IBEX data, appeared to be considerably more compact and rounded than the teardrop model predicted. This led a group of researchers, led by physicist Merav Ofer and her colleagues, to propose an alternative. They called it the croissant model, and it was not a metaphor chosen for its elegance. The heliosphere, they argued, actually resembles the curved, lobed shape of a croissant, with two broad lobes extending to the sides, rather than one long tail extending behind. The croissant model emerged from a more careful treatment of the role of the Sun's magnetic field in shaping the outer heliosphere. The Sun's magnetic field, carried outward by the solar wind, does not simply fill the heliosphere uniformly. It has structure. At the solar equator, the field is primarily toroidal, wrapping around the Sun in a spiral. At the poles, the field lines run more radially outward. As the solar wind carries these field lines to the outer heliosphere, and they pile up near the heliopause, the magnetic pressure is not evenly distributed. The equatorial field lines, more tightly wound and carrying more magnetic pressure, tend to concentrate near the sides of the heliosphere, rather than pushing straight back into a tail. The result, when the mathematics is worked out carefully, is not a teardrop, but something more complex, more lobed, more like two broad rounded extensions flanking the solar equatorial plane, rather than one long trailing structure. The croissant, asymmetric, structured by magnetic forces as much as by the simple physics of a moving object pushing through a medium. Not everyone in the field accepts the croissant model. Science is rarely that clean, and the heliosphere is no exception. Other research groups have continued to argue for versions of the elongated tail model, pointing to different analyses of the IBEX data and to magnetohydrodynamic simulations that still produce tail-like structures under certain assumptions about the interstellar magnetic field, strength and direction. The honest picture of the scientific consensus is that the teardrop model of the 1980s is almost certainly too simple, that some form of more rounded or lobed structure is better supported by the current data, and that the precise shape of the heliosphere, particularly on the trailing side, remains actively debated. We have sent 2 spacecraft through the heliosphere, but both of them travelled roughly in the same general hemisphere, both heading outward from the front and side of the heliosphere rather than from the trailing tail region. The tail side of our cosmic home has never been directly sampled by any instrument. We are still, in a very real sense, arguing about a part of the heliosphere we have never touched. What the shape debate reveals, beyond its immediate scientific content, is something deeper about the nature of the heliosphere itself. The shape of a bubble in a flowing medium is not just an aesthetic feature. It encodes information about the forces acting on it, the pressure of the medium, the strength and direction of the magnetic field, the speed and power of the solar wind. A perfectly round heliosphere would mean that the interstellar medium exerts equal pressure from all sides, and that the Sun's magnetic field plays little role in shaping the outer boundary. A strongly elongated teardrop would mean the ram pressure of the Sun's motion through the galaxy dominates everything else. The croissant shape, if confirmed, would mean that the Sun's magnetic field is a primary architect of the outer heliosphere, competing with and in some regions dominating the effects of the interstellar pressure and the Sun's motion. The shape is, in other words, a diagnostic of the physics, and getting it right matters not just for our understanding of the solar system, but for our understanding of how all stellar systems interact with the interstellar medium around them. There is another layer to the shape question that rarely gets mentioned in popular accounts, but that I find genuinely remarkable. The shape of the heliosphere affects how it shields the inner solar system from galactic cosmic rays. A longer tail would provide additional shielding from certain directions, funneling cosmic rays around the sides and reducing the flux that reaches Earth from behind the solar system's direction of motion. A more rounded or croissant-shaped heliosphere would distribute the shielding differently, potentially allowing more cosmic ray penetration from certain angles. The exact biological and geological effects of different heliospheric shapes are still being worked out, but the implication is striking. The shape of the invisible bubble surrounding our solar system may have influenced the intensity of cosmic radiation reaching Earth over geological timescales, as the heliosphere's shape has changed with the Sun's varying activity and with the varying density of the interstellar medium through which the solar system has moved over billions of years. The shape of the heliosphere is not just a question for physicists. It is a question that touches, however distantly, the history of life on Earth. And there is one more dimension to the shape question that opens a door we will spend more time behind later in our journey tonight. The heliosphere's shape is determined partly by what is outside it, by the pressure, the density, the magnetic field, and the overall character of the interstellar medium that surrounds us. If the heliosphere is not the shape the textbooks showed, it is partly because the interstellar environment outside it is not what the textbooks assumed. The interstellar medium pressing in on our heliosphere from every side is not a uniform, featureless background. It is a specific region of space with its own structure, its own history, and its own properties that differ measurably from the galactic average. We are not floating in generic interstellar space. We are embedded in something particular, something with a name. And understanding what that something is and what it means for the future of our solar system is one of the most extraordinary stories in all of modern astronomy. There is a question that almost nobody thinks to ask, and yet it changes everything once you hear it. We talk about the solar system moving through space. We talk about the sun carving a path through the galaxy at roughly 43,000 miles per hour, dragging its planets and its heliosphere along with it, ploughing through whatever occupies the space between the stars. But what exactly is it ploughing through right now, at this precise moment in cosmic time? The answer is not empty space. The answer is not a uniform interstellar medium spread evenly across the galaxy like a thin gas filling every corner equally. The answer is something specific, something local, something with a name and a shape and a set of physical properties that differ measurably from the galactic average. Right now, tonight, as you lie in the dark and listen to these words, the entire solar system is passing through a diffuse cloud of warm plasma and neutral gas that astronomers call the local interstellar cloud. And we've been inside it for somewhere between 45,000 and 150,000 years. We will exit it, according to current estimates, somewhere between the next few thousand years and the next few tens of thousands of years. And when we do, the heliosphere and everything it protects may change in ways that are difficult to fully predict. The local interstellar cloud is not a cloud in the way you might picture one. It is not dense, it is not dark. It is not something you could see if you were travelling through it, which of course we are. It is extraordinarily diffuse, a wisp of warm ionized and neutral gas with an average density of about 0.3 atoms per cubic centimetre. To put that in perspective, the air you are breathing right now contains roughly 27 million trillion atoms per cubic centimetre. The local interstellar cloud is almost incomprehensibly emptier than that, and yet it is not nothing. Compared to the very cold and slightly denser neutral gas that fills much of the surrounding interstellar medium, the local interstellar cloud is warmer, at roughly 6,000 to 10,000 degrees Kelvin, and is partially ionized, meaning a significant fraction of its hydrogen and helium atoms have been stripped of their electrons. This warmth and ionization are what give the cloud its character and what make it distinct from the broader interstellar environment in which it sits. The cloud itself is part of a larger structure called the local bubble, a vast region of very hot, very low density plasma that extends roughly 300 light-years in most directions around the Sun. The local bubble is thought to have been carved out by a series of supernova explosions that occurred in this region of the galaxy millions of years ago. Those stellar detonations blasted the surrounding interstellar medium outward, leaving behind a cavity of hot, thin plasma. Inside that cavity, smaller, denser clouds drift like wisps of fog in an otherwise clear room. The local interstellar cloud is one of these wisps. It is a remnant, a condensation, a fragment of denser material that survived the ancient supernova blast waves and has been slowly drifting through the local bubble ever since. And the solar system, by a coincidence of galactic timing, is currently passing through it. What does it mean for the heliosphere to be embedded in a specific cloud rather than in generic interstellar space? It means that the pressure, density, magnetic field strength, and temperature of the medium pressing in on the heliopause are determined by the properties of the local interstellar cloud, rather than by some average interstellar value. The heliosphere's size, shape, and shielding effectiveness are all sensitive to the external pressure pushing in on it. A denser or more magnetically intense surrounding medium would compress the heliosphere inward, shrinking the termination shock, reducing the volume of the heliosheath, and potentially allowing more galactic cosmic rays to penetrate closer to the inner solar system. A less dense medium would allow the heliosphere to expand outward, pushing the heliopause further from the Sun. Right now, the properties of the local interstellar cloud are holding the heliopause at roughly 100 to 120 astronomical units from the Sun. But that number is not fixed for all time. It changes as the Sun's activity varies, and it would change significantly if the external medium changed. Here is what makes this genuinely important, and in a quiet way, genuinely unsettling. We know that the solar system has not always been inside the local interstellar cloud. For most of the last several 100,000 years, the solar system was passing through a different region of the local bubble, one with different properties. And in the distant past, the solar system has passed through much denser interstellar clouds, regions where the external pressure on the heliosphere was dramatically higher than it is today. Some researchers have modelled what happens to the heliosphere when the solar system passes through a dense interstellar cloud. The results are striking. In the densest scenarios, the heliosphere could shrink dramatically, with the heliopause moving inward to within a few tens of astronomical units of the Sun, potentially inside the orbit of Neptune. In the most extreme cases, some models suggest the galactic cosmic ray environment inside the compressed heliosphere could intensify significantly, exposing the Earth's atmosphere and surface to radiation levels substantially higher than what we experience today. These are theoretical models, and the uncertainties are enormous, but the basic physics is well understood. The heliosphere's size and shielding capacity depend on external pressure. External pressure has varied throughout the solar system's history, and the consequences of those variations may have left marks on the geological and biological record of our planet. The question of what happens when the solar system exits the local interstellar cloud is one that researchers are actively working on. Current models suggest the cloud's edge is somewhere close, in cosmic terms, possibly within a few thousand astronomical units of the heliopause in some directions, possibly already being grazed by the heliosphere in certain regions. When the solar system emerges from the cloud and re-enters the surrounding local bubble plasma, the external pressure on the heliosphere will drop significantly, because the local bubble plasma is even less dense than the local interstellar cloud. The heliosphere may expand outward. The termination shock may move further from the Sun. The precise effects on cosmic ray shielding, on the flux of interstellar material entering the inner solar system, and on the overall structure of the heliosphere are still being modelled and debated. We do not know exactly when the exit will happen. We do not know precisely what the heliosphere will look like on the other side of that exit. And we have no instrument currently in a position to watch it happen in real time. Let that thought settle in for a moment, because I find it one of the most quietly remarkable facts in all of this story. We are inside a cloud, a specific named, physically distinct region of interstellar space that the solar system entered tens of thousands of years ago, around the time that modern human beings were beginning to spread across the planet, painting animals on cave walls and looking up at the same night sky you can see tonight. We entered this cloud somewhere in humanity's deep prehistory. We will exit it sometime in the future, possibly before our civilization has aged another 10,000 years. The entire span of recorded human history, every civilization from ancient Mesopotamia to the present day, has taken place inside this cloud. And when we leave it, the solar system will be a slightly different place, with a slightly different heliosphere pressing against a slightly different interstellar environment. The fog we are flying through is not just a physical structure, it is a chapter in the solar system story. And the next chapter, whatever it brings, is closer than most people will ever stop to realize. We have spent a great deal of time tonight traveling outward together, from the familiar warmth of the inner solar system, through the gas giant planets, past the termination shock and the churning heliosheath, across the heliopause and into the interstellar medium beyond. And if you have been keeping the scale in mind, you already know that the distances involved are almost too large to hold. The heliopause, that final boundary of the sun's direct influence, sits roughly 120 astronomical units from the sun. 120 times the distance from the Earth to the sun. A number so large that Voyager 1, travelling at about 38,000 miles per hour, took 35 years to reach it. But here is the thing I have been waiting to tell you, the thing that resets the scale completely and forces you to reconsider everything you thought you understood about how far the solar system extends. The heliopause is not the edge of the solar system, not even close. Beyond the heliopause, far beyond it, in a region so remote that no spacecraft has ever entered it and no telescope has ever directly imaged it, lies a structure so vast that it wraps the entire solar system in a shell of ancient ice and rock, extending nearly a quarter of the way to the nearest star. It is called the Oort cloud, and almost everything we know about it is inferred rather than observed. The Oort cloud was first proposed in 1950 by the Dutch astronomer Jan Hendrik Oort, who noticed something strange about the long-period comets that occasionally fall inward through the solar system and pass close to the sun. These comets, the ones with orbital periods of hundreds or thousands or even millions of years, appear to come from all directions in the sky, with roughly equal frequency. Not from the plane of the solar system, where the planets orbit, and where the Kuiper belt sits, from everywhere, from above and below the solar plane, from all angles. That random directional distribution implied that their source was not a flat disk but a sphere, an enormous spherical shell of objects surrounding the solar system in every direction. Oort calculated that this shell would need to extend from roughly 2,000 astronomical units from the sun out to perhaps 100,000 astronomical units or more. That outer edge, at 100,000 astronomical units, is roughly 1.6 light-years from the sun. The nearest star system, Alpha Centauri, is about 4.2 light-years away. The Oort cloud reaches roughly a quarter of the distance to our nearest stellar neighbour. Think about what that means for a moment. We speak of the solar system as if it is a compact, bounded thing. 8 planets, some moons, an asteroid belt, a Kuiper belt, and then space. But the gravitational reach of the sun extends roughly halfway to Alpha Centauri, halfway to the nearest star. The solar system, in its true extent, is not a small neighbourhood in the galaxy. It is a vast gravitational domain, and its outermost territory is a shell of material so thinly spread across such an enormous volume of space that a traveller passing through it would almost certainly never notice. The objects in the Oort cloud are not tightly packed. They are separated from each other by enormous distances. The total mass of all the material in the Oort cloud is estimated to be somewhere between 1 and 40 times the mass of the Earth, distributed across a volume of space that dwarfs anything in the inner solar system. It is one of the most enormous and most thinly populated structures in the solar system, and we have never seen a single one of its objects directly. Every piece of evidence for the Oort cloud is indirect. It comes from the comets themselves, those ancient icy visitors that occasionally fall inward and streak across our sky with their bright tails pointing away from the sun. When astronomers calculate the original orbital parameters of long-period comets, tracing their paths back to their source regions using orbital mechanics, they consistently find origins in the distant cloud that Oort described. The cloud's inner edge, sometimes called the inner Oort cloud or the Hills cloud, after the astronomer who proposed its existence in 1981, may begin as close as 2,000 astronomical units from the Sun. The outer edge, where the Sun's gravity weakens to the point where passing stars and the general gravitational field of the galaxy can perturb the orbits of objects, extends to that enormous distance of up to 100,000 astronomical units. Between those two boundaries lies a population of objects estimated in the trillions. Trillions of icy bodies ranging in size from small pebbles to objects potentially hundreds of kilometers across, slowly orbiting the Sun in nearly circular paths so far from home that a single orbit takes millions of years to complete. The Oort cloud is not static. It is being continuously disturbed by forces from outside the solar system. Passing stars which drift within a light year or two of the solar system over timescales of millions of years gravitationally nudge the outer cloud, perturbing the orbits of objects and sending some of them falling inward toward the Sun on long, elliptical paths. The gravitational influence of the galactic tide, the overall gravitational field generated by the mass of the Milky Way galaxy itself, also stirs the Oort cloud continuously, warping the outer orbits and providing a steady rain of new cometary material into the inner solar system. This is where long-period comets come from. They are Oort cloud objects that have been nudged onto new trajectories by a passing star or the galactic tide, falling inward for the first time in millions of years, preserving in their ice a chemical record of the early solar system from 4.5 billion years ago. Why does this matter for tonight's story, for our journey to the edge of the solar system? Because the Oort cloud represents something profound about the nature of the boundary we have been exploring. The heliopause, the boundary of the heliosphere, is real and measurable and confirmed by direct spacecraft data. But it is not the gravitational edge of the solar system. The Sun's gravity, that fundamental force that holds the planets in their orbits and anchors the entire structure of the solar system, reaches far beyond the heliopause. It reaches into the Oort cloud. It holds trillions of ancient icy objects in slow gravitational embrace across distances that make the heliopause seem trivially close. The solar system has layers within layers, boundaries within boundaries, and the deeper you look, the further the reach of our star extends into the surrounding darkness. And there is one more dimension to the Oort cloud that I want to leave you with before we move on. The Oort cloud is not just a reservoir of comets, it is a record. The objects in the outer Oort cloud have been sitting in their distant orbits for billions of years, largely undisturbed, preserving the chemical composition of the primordial solar nebula in their ice. They are time capsules, frozen samples of the material from which everything in the solar system formed, including the water in your body and the carbon in your cells. When a long-period comet falls inward and passes close to Earth, it is carrying material that has been frozen in the dark at the edge of the solar system since before the Earth existed. That material may have played a role in seeding the early Earth with water and organic molecules. The outermost, most remote, most mysterious region of the solar system may have contributed directly to the conditions that made life on this planet possible. The edge is not separate from the center. It is connected to it intimately across billions of miles and billions of years. There is a particular kind of discovery in astronomy that does not begin with a telescope. It begins with mathematics, with an astronomer sitting at a desk, staring at a set of numbers that do not add up, and realizing that the only way to make them add up is to assume that something exists which no one has yet seen. This is how Neptune was discovered in 1846, predicted mathematically from the anomalous motion of Uranus before anyone pointed a telescope at the right patch of sky and confirmed it was there. It is one of the most elegant demonstrations in the history of science that the universe is governed by laws precise enough that we can infer the existence of invisible objects from the behavior of visible ones. And today, in the outer reaches of the solar system, something very similar may be happening again. A growing body of orbital data from the most distant known objects in the solar system suggests that something large, something very far away, and something entirely unseen is gravitationally influencing the architecture of the outer solar system. Astronomers call it Planet 9, and if it exists, it would be one of the most significant discoveries in the history of planetary science. The story of Planet 9 begins with a group of small icy objects known as trans-Neptunian objects, bodies that orbit the Sun beyond Neptune, in the outer reaches of the Kuiper Belt and beyond. Most of these objects have orbital parameters that are relatively easy to explain through the gravitational influence of the known planets. But starting in the early 2010s, astronomers surveying the far outer solar system began noticing something strange about a specific subset of the most distant trans-Neptunian objects, those with orbital periods of thousands of years and perihelia. Their closest approach points to the Sun, well beyond Neptune. These objects were not randomly distributed in their orbits. Their orbital planes were clustered. The long axes of their elliptical orbits, their arguments of perihelion, were bunched together in a way that should not occur by chance. If you threw darts blindfolded at a celestial sphere, the orbital orientations of distant objects should be scattered randomly across all possible angles. Instead, these objects were pointing, collectively, in roughly the same direction. Something was herding them. In 2016, astronomers Konstantin Batygin and Michael Brown at the California Institute of Technology published a paper that attempted to explain this clustering mathematically. They ran computer simulations of the outer solar system, testing whether the known planets could produce the observed orbital clustering through their combined gravitational influence. They could not. The clustering was too pronounced, too statistically significant to be a product of known gravitational sources or observational bias. But when Batygin and Brown added a hypothetical additional planet to their simulations, a planet with specific orbital characteristics, the clustering fell naturally out of the mathematics. The hypothetical planet they described would need to have a mass roughly 5 to 10 times that of Earth. It would orbit the Sun at an average distance of perhaps 400 to 800 astronomical units, far beyond the Kuiper Belt, on a highly elliptical orbit inclined significantly relative to the plane of the other planets. Its orbital period would be somewhere between 10,000 and 20,000 years. It would be extraordinarily cold, receiving almost no sunlight at those distances. And it has never been directly observed, because at that distance, even a planet 10 times the mass of Earth would be almost impossibly faint. The reaction to the Batygin and Brown paper was immediate and divided. Some astronomers found the clustering evidence compelling and accepted the Planet 9 hypothesis as a serious scientific proposition worthy of intensive search efforts. Others were more skeptical, arguing that the clustering might be a product of observational bias, since the distant trans-Neptunian objects we have found so far represent only a tiny, possibly non-representative sample of all the objects in the outer solar system. Finding distant trans-Neptunian objects requires dedicated sky surveys with large telescopes, and the parts of the sky that have been most thoroughly surveyed are not randomly distributed. The objects we have found could be clustered not because of a hidden planet, but simply because we have looked more carefully in some directions than others. This debate has continued in the years since the original paper, with new surveys adding more distant objects to the sample and new analyses arguing both for and against the statistical significance of the clustering signal. If Planet 9 exists, where is it right now? That question has motivated intensive sky searches since 2016. Several major observatories, including the Subaru telescope in Hawaii, have dedicated significant observing time to scanning the outer solar system for a faint moving point of light against the background stars. So far, no confirmed detection has been made. This is not necessarily surprising. Planet 9, if it exists, is likely near the farthest point of its elongated orbit, where it moves most slowly and is hardest to detect against the background sky. At 400 to 800 astronomical units, it would reflect so little sunlight that it would be among the faintest objects detectable by current instrumentation. The search continues, and the next generation of sky surveys, including the Vera Rubin Observatory in Chile, which began operations in the mid-2020s with an unprecedented ability to detect faint-moving objects, may finally either confirm or rule out Planet 9 within the coming years. But here is the thing I find most interesting about Planet 9, beyond the immediate question of whether it exists. If it does exist, its presence would require an explanation for how it got there. A planet 5 to 10 times the mass of Earth does not simply appear in a distant, elongated orbit around the Sun without a history. The leading theories involve a scenario in which Planet 9 formed much closer to the Sun, perhaps in the region of the giant planets, and was then gravitationally scattered outward by an interaction with Jupiter or Saturn early in the solar system's history, eventually settling into its current distant orbit through a combination of interactions with the primordial outer solar system and the gravitational influence of passing stars. This scenario is not implausible. Planet scattering was a common event in the early solar system, and the discovery of similar distant giant planets in eccentric orbits around other stars supports the idea that this kind of scattering happens regularly. Planet 9 may be a survivor of the solar system's violent early history, flung to the outer darkness and forgotten for 4.5 billion years. There is also a more unsettling possibility that some researchers have floated, one that sits at the edge of current scientific credibility, but that I think deserves a mention precisely because of where we are in tonight's journey. Some astronomers have suggested that Planet 9 may not have formed in the solar system at all. In the early solar system, the Sun formed in a star cluster alongside hundreds or thousands of sibling stars that have since dispersed throughout the galaxy. During the cluster phase, stars passed much closer to one another than they do today, and gravitational interactions between stellar systems were far more common. It is theoretically possible, under certain conditions, that the early Sun could have captured a free-floating planet, a rogue world drifting through the cluster without a parent star, and retained it in a distant orbit. If Planet 9 is a captured world, then the object pulling gravitationally on the orbits of distant Kuiper belt bodies, the hidden architect of the outer solar system, is not even originally from our solar system. It is an interloper from the wider galaxy, bound to our Sun by the accident of an ancient gravitational encounter, sitting in the dark at the edge of everything we call home. That possibility has not been ruled out, and it is, in the quietest and most extraordinary way, terrifying. You are being bombarded right now, not by anything you can feel, not by anything visible or audible or in any way detectable by your senses, but at this very moment, as you lie still and listen to these words, high-energy particles are passing through your body at very nearly the speed of light. They stream down from the sky in every direction, passing through the roof above you, through the walls around you, through the mattress beneath you, and through your body itself, as if none of it were there at all. They are called galactic cosmic rays, and they are among the most energetic particles in the known universe. They come from supernovae, from the violent jets of active galaxies, from the shock waves of stellar explosions, happening in distant corners of the Milky Way. They have been travelling for thousands or millions of years before they reach you. And the reason the flux of cosmic rays striking you right now is not dramatically higher, the reason life on Earth has been able to develop and persist for billions of years in a galaxy filled with these deadly particles, is the heliosphere. The invisible bubble we have been exploring tonight is not just a scientific curiosity, it is a shield, and without it, everything on the surface of this planet would be exposed to a radiation environment that would look very different from what biology has adapted to survive. To understand what galactic cosmic rays actually are, it helps to start with what they are not. They are not rays in the traditional electromagnetic sense, not light or X-rays or gamma rays, though those forms of radiation certainly exist in space as well. Galactic cosmic rays are primarily charged particles, protons, helium nuclei, and heavier atomic nuclei, stripped of their electrons and accelerated to extraordinary energies by the violent processes that produce them. The most energetic galactic cosmic rays carry energies that dwarf anything produced by particle accelerators on Earth. A single proton can carry the kinetic energy of a baseball thrown at 100 miles per hour, concentrated into a particle smaller than any object human hands have ever built. When particles like that strike the upper atmosphere, they produce cascades of secondary particles, showers of pions and muons, and other subatomic fragments that rain down through the atmosphere and reach the ground. Some of those secondary particles are the ones passing through you right now. The heliosphere's role as a cosmic ray shield operates on several levels. At the outermost boundary, the heliopause itself acts as a partial barrier, deflecting and absorbing some fraction of the incoming galactic cosmic ray flux. The interstellar magnetic field outside the heliopause guides cosmic rays along field lines that often run tangentially to the heliosphere's surface rather than directly inward, reducing the fraction that penetrate the boundary. Once inside the heliosphere, cosmic rays face additional obstacles. The solar wind, streaming outward at high speed with its embedded magnetic field, acts as a kind of conveyor belt running in the opposite direction to the incoming cosmic rays, slowing their inward propagation and scattering them away from the inner solar system. This effect, known as solar modulation, is measurable and significant. During periods of high solar activity, when the solar wind is stronger and more turbulent, the cosmic ray flux reaching Earth drops noticeably. During solar minimum, when the wind is weaker, more cosmic rays slip through to the inner solar system. The Voyager spacecraft provided the first direct measurement of the cosmic ray environment across the heliospheric boundary, and the numbers they returned were striking. As Voyager 1 moved through the heliosheath toward the heliopause, the instruments recorded a gradual increase in galactic cosmic ray intensity. The closer it got to the boundary, the more cosmic rays it detected, exactly as expected from the theory that the heliosphere was shielding the inner solar system from these particles. And then, in the days surrounding the heliopause crossing in 2012, the cosmic ray count jumped sharply. Within a very short distance of crossing into interstellar space, the galactic cosmic ray flux measured by Voyager 1 increased by roughly 70% compared to what it had been deep inside the heliosphere. 70% more galactic cosmic radiation on the other side of that invisible boundary than on our side. The heliosphere was not blocking all cosmic rays, but it was blocking a very substantial fraction of them, and that fraction matters enormously for the habitability of the inner solar system. What would Earth look like without the heliosphere's shielding? This is not an idle thought experiment. It is a question with real scientific answers, derived from multiple lines of evidence, One source of evidence comes from the geological record. Scientists can measure the flux of certain cosmogenic isotopes, atoms produced when galactic cosmic rays strike the atmosphere, and nuclei in surface rocks, in ice cores and rock samples. These isotopes accumulate at rates that depend on the cosmic ray flux, and by measuring their abundance in ancient samples, scientists can reconstruct how the cosmic ray environment at Earth's surface has changed over time. The record shows variations that correlate with changes in solar activity and over longer timescales with changes in the solar system's position relative to the galactic plane. Periods when the cosmic ray flux was higher have left detectable signatures in the isotopic record. The shielding provided by the heliosphere is not uniform through time, and its variations have left marks in Earth's history that scientists are still working to fully interpret. A more dramatic example comes from a different source entirely. There are stars in the galaxy that have lost their equivalent of a heliosphere, or that produce stellar winds far weaker than the Sun's, leaving their planetary systems exposed to the full galactic cosmic ray environment. For planets orbiting these stars, the cosmic ray flux at the surface could be significantly higher than what Earth experiences. High cosmic ray fluxes have complex effects on planetary atmospheres and on the chemistry of planetary surfaces. They can ionize atmospheric gases, produce reactive chemical species, damage DNA and other organic molecules, and potentially disrupt the atmospheric chemistry in ways that affect climate and habitability. None of this means that life is impossible under higher cosmic ray conditions. Evolution is remarkably adaptable, but it does mean that the heliosphere is not a passive background feature of the solar system. It is an active component of the system of conditions that make Earth the kind of place where complex life has been able to flourish for billions of years. There is something I want you to sit with for a moment, because I think it deserves more than a passing thought. The heliosphere has been the solar system's shield for as long as the sun has been blowing its solar wind, which is essentially the entire 4.5 billion year history of the solar system. During that time, life on Earth has evolved from single-celled organisms in ancient oceans to the extraordinary complexity of the biosphere we inhabit today. That evolution happened under a specific cosmic ray environment, shaped and modulated by the heliosphere's shielding. The pace of mutation, the rate of genetic change, the very tempo of evolution may have been influenced by the flux of cosmic radiation reaching the Earth's surface. And that flux has been continuously regulated by the invisible bubble of solar wind surrounding us. When you think about the heliosphere, not just as a physical structure, but as a participant in the story of life on Earth, the edge of the solar system begins to feel a great deal closer to home than the number 120 astronomical units might suggest. The boundary is distant. Its effects reach all the way to the cells in your body. Voyager 1 and Voyager 2 were never designed to study the heliosphere's boundary. They were designed to study planets. The fact that they survived long enough to cross the heliopause and return data from interstellar space is one of the most extraordinary accidents of longevity in the history of space exploration. Their instruments were chosen for planetary science, not heliospheric physics. Several of the most important instruments for studying the boundary region had failed years or decades before the crossings occurred. The plasma science instrument on Voyager 1 stopped functioning in 1980, 32 years before the heliopause crossing that it should have been there to measure directly. The result is that our two pieces of direct evidence from interstellar space are incomplete, collected by aging instruments never meant for this purpose, in only two directions out of the infinite number available, spread decades apart in time. What the scientific community has been calling for with increasing urgency since the early 2010s is a mission designed from the ground up to study the heliosphere's boundary and the local interstellar medium in a deliberate, comprehensive, and scientifically optimized way. That mission has a name. It is called the Interstellar Probe, and it represents perhaps the most ambitious deep space science mission ever seriously proposed by NASA. The concept for the Interstellar Probe has been developed through years of community planning and scientific deliberation, with a major milestone coming in the 2022 Planetary Science and Astrobiology Decadal Survey, the influential document produced every 10 years in which the scientific community collectively prioritizes its most important goals for the coming decade. The Interstellar Probe was identified as a high-priority large mission concept, though not yet fully approved and funded, reflecting broad consensus in the heliospheric and planetary science communities that the time has come to send a purpose-built spacecraft to the edge of the solar system and beyond. The vision is ambitious. A spacecraft launched no earlier than the mid-2030s, using a gravity assist from Jupiter similar to the technique that accelerated the Voyager spacecraft, but with a more powerful launch vehicle and a more optimized trajectory, aimed at reaching the heliopause within roughly 15 years of launch and continuing into the local interstellar medium for decades afterward. The scientific goals of the Interstellar Probe are both broader and deeper than anything the Voyager missions achieved. Where Voyager 1 sampled the heliosphere in a single direction above the solar plane, the Interstellar Probe would be aimed in a different direction, potentially toward the nose of the heliosphere, the leading edge in the direction of the Sun's motion through the galaxy. This is perhaps the most scientifically important direction to sample, because it is where the collision between the solar wind and the interstellar medium is most direct and most energetic, and where the boundary structures are expected to be most pronounced. Having direct measurements from the nose direction, combined with the existing Voyager data from two other directions, would allow scientists to triangulate the three-dimensional structure of the heliosphere in a way that has never been possible from indirect observations alone. The instrument suite planned for the Interstellar Probe represents a generational leap beyond what the Voyager spacecraft carried. Modern plasma detectors can measure particle velocities, directions, and energy distributions with a precision that the 1970s instruments could not approach. Modern magnetometers are more sensitive, more stable, and capable of resolving finer structures in the magnetic field. Neutral atom imagers, the technology that IBEX demonstrated so powerfully from Earth orbit, would allow the Interstellar Probe to map the heliospheric boundary in energetic neutral atoms from multiple vantage points during its outward journey, building a three-dimensional picture of the boundary structure as the spacecraft moves through it. Dust detectors would measure the properties of interstellar dust grains, those tiny particles that carry information about the chemical composition of the interstellar medium and potentially about the broader galactic environment. And a plasma wave instrument would measure the density and temperature of the plasma in the heliosheath and the local interstellar medium with a precision that addresses the most significant gaps left by the Voyager data. One of the most exciting scientific objectives of the Interstellar Probe, and one that distinguishes it most sharply from the Voyager missions, is the possibility of imaging the heliosphere from the outside. As the spacecraft moves outward through the heliosheath and eventually beyond the heliopause, its neutral atom images could potentially turn back toward the inner solar system and capture images of the heliosphere's structure from the outside. The first such view in human history. Imagine standing far enough from your house to see its entire shape for the first time. Not just the wall directly in front of you, but the roof and the sides and the back. The complete three-dimensional form. That is what the Interstellar Probe might be able to do for the heliosphere. Scientists could compare those outside images with the theoretical predictions of the croissant model, the elongated tail model, and every other proposed shape, and determine definitively which one is correct. The shape debate that has occupied heliospheric physicists for more than a decade might finally be resolved by a single image sent back from beyond the edge. The engineering challenges of the interstellar probe are enormous, and in some ways they have not changed fundamentally since the Voyager era. Power remains the critical constraint. Nuclear power sources decay over time, and a mission designed to last 50 years or more must either accept decreasing power over the mission duration or develop new radioisotope power technologies capable of maintaining adequate power output for longer than any previous deep space mission. Communication is equally challenging. At 200 or 300 astronomical units from the Sun, the signal from the spacecraft would be even fainter than the current Voyager signals. Maintaining a reliable data link at those distances will require either larger antennas on the spacecraft, improved low-noise receivers on the ground, or both. And the spacecraft must survive a radiation environment, a thermal environment, and a mechanical stress environment across 5 or more decades of operation, during which no repair or maintenance of any kind is possible. Every component must be right the first time. Every system must be robust enough to last longer than some human careers. But beyond the engineering and the science objectives, the interstellar probe carries a significance that is harder to quantify and easier to feel. It represents a deliberate choice to go back. Not by accident, not as a lucky consequence of a planetary tour that ran long, but on purpose, with intention, with instruments designed for the journey from the beginning. It says that humanity, having received the first tantalizing data from the edge of the solar system through the Voyager spacecraft, has decided that what was found there is important enough to deserve a dedicated return. The heliosphere's boundary, the ribbon, the asymmetric termination shock, the semi-permeable heliopause, the unexpected magnetic field behavior, the structured local interstellar medium pressing in from outside. All of these mysteries are deemed significant enough to send another machine into the dark. A smarter machine, a more capable machine, aimed more precisely at the questions that the Voyager data raised but could not answer. That choice, when it is finally made and funded and committed to, will be one of the clearest statements the scientific community has ever made about the importance of understanding not just what is out in the universe at large, but what is right here, at the very edge of home. There is a particular kind of silence that settles in at the edge of understanding. Not the silence of ignorance where you do not know enough to know what questions to ask, but the silence of a frontier, where you know exactly what the question is, where you can trace its outline with precision, where you can point to the specific measurements and say, here, this is where our knowledge ends and the unknown begins. That is where heliospheric science sits tonight. After 5 decades of data from the Voyager spacecraft, after years of full sky maps from IBEX, after generations of theoretical work and computational modelling and careful analysis, scientists know enough about the edge of the solar system to identify very clearly what they do not know. And what they do not know is, in some ways, more extraordinary than everything they have confirmed. There is a question buried in the data, one that the existing evidence suggests, but cannot yet conclusively answer. And it is the kind of question that, if answered in the way some researchers suspect it might be, would change the way we understand the solar system's place in the galaxy in a very fundamental way. Let us approach it carefully, the way the data approaches it, from the sides rather than directly. Start with the asymmetry. We have discussed the fact that the heliosphere is not the same size in every direction, that Voyager 1 and Voyager 2 cross the termination shock and the heliopause at different distances. We have discussed the ribbon discovered by IBEX, running perpendicular to the local interstellar magnetic field. We have discussed the croissant shape hypothesis and the evidence that the interstellar magnetic field plays a significant role in shaping the outer heliosphere. Now put these things together and ask a slightly different question. Not just what is the shape of the heliosphere, but why is it that shape? And what does that shape tell us about the specific interstellar environment pressing in from outside? Because here is what the combined data suggests, quietly, in the way that data suggests things before the community has reached a consensus. The interstellar medium immediately surrounding our heliosphere is not uniform. It is not smooth, it appears to be structured. And the question that the data cannot yet answer with certainty is whether that structure is the passive result of the solar system's motion through the local interstellar cloud, or whether it reflects something more organized, more directional, more architecturally significant about the space that immediately surrounds us. The local interstellar magnetic field is part of this puzzle. IBEX's ribbon established that the field runs in a specific direction relative to the heliosphere, threading through the surrounding interstellar medium in a way that leaves a visible imprint on the heliosphere's boundary. But the local interstellar magnetic field is not just a background feature, it is connected to the larger structure of the galactic magnetic field, which itself reflects the history of the galaxy's star formation, supernova explosions, and the large-scale dynamics of the interstellar medium over billions of years. The solar system is not sitting in a random, unstructured patch of interstellar space. It is sitting in a specific location in the Orion arm of the Milky Way, inside the local bubble, inside the local interstellar cloud, with the interstellar magnetic field running in a specific direction around it. All of these facts are known. What is not yet known with confidence is how these layers of structure interact with each other and with the heliosphere in a coordinated way, and whether the patterns we see in the heliospheric boundary data are encoding a picture of that surrounding structure that we have not yet learned to read correctly. Then there is the energy problem. One of the persistent difficulties in heliospheric modelling is what scientists sometimes call the missing pressure problem. The Voyager spacecraft measured the properties of the heliosheath plasma directly, and those measurements, when combined with the known properties of the solar wind feeding into the heliosheath from inside, do not quite balance energetically. There is more pressure holding the heliosphere in its observed configuration than the measured solar wind and interstellar medium pressures alone seem able to provide. Something is contributing additional pressure, additional energy to the boundary region, and the source of that extra pressure is not clearly identified. Some researchers have proposed that a population of energetic particles, not well sampled by the Voyager instruments, is supplying the missing pressure. Others have suggested that the interstellar magnetic field outside the heliopause is stronger than current measurements indicate, providing additional magnetic pressure that the models have underestimated. Neither explanation is fully satisfying yet. The numbers do not cleanly close, and in physics, when the numbers do not close, something is missing from the accounting. There is also the matter of what is happening just outside the heliopause in the region scientists call the outer heliosheath, or the hydrogen wall. As neutral hydrogen atoms from the interstellar medium approach the heliopause, they begin to interact with the outflowing solar wind protons through charge exchange, building up a region of slightly denser, slightly warmer neutral hydrogen just outside the heliopause boundary. This hydrogen wall has been detected in ultraviolet observations of the Sun and of other nearby stars, and its properties tell scientists something about the conditions of the interstellar medium in the immediate vicinity of the heliosphere. But the detailed structure of the hydrogen wall, the way it varies around the heliosphere's surface, the way it responds to changes in the solar wind and the interstellar environment, is something that existing data describes only in outline. The Voyager spacecraft do not carry the instruments needed to characterize the hydrogen wall directly, and the indirect measurements from Earth orbit can tell you that it exists and roughly where it is, but not what it looks like in detail or how it behaves dynamically over time. All of these threads, the asymmetry, the ribbon, the missing pressure, the structured interstellar environment, the hydrogen wall, converge on a single, unresolved question. Is the space immediately surrounding our heliosphere simply the passive, somewhat variable interstellar medium that the solar system happens to be moving through, shaped by distant supernova and the slow drift of interstellar clouds? Or is the environment around our heliosphere shaped in some additional way by the heliosphere's own presence, by the pressure it exerts outward, by the neutral atoms and energetic particles it leaks into the surrounding medium, by the bow wave or deflection structure it produces as it moves through the local interstellar cloud? In other words, is the heliosphere purely a passenger in its interstellar environment, or is it also a sculptor of that environment, actively reshaping the space immediately around it in ways that feed back on the boundary and complicate everything we are trying to measure? The honest answer is that we do not know. The data suggests both possibilities are at least partially true, and the current generation of instruments and models is not sufficient to fully distinguish between them. What we can say with confidence is this: the boundary of the solar system is not a simple passive edge. It is an active, dynamic, incompletely understood interface between our star and the galaxy. It is shaped by forces from inside and outside simultaneously. It has structures we did not predict. It has properties we cannot yet fully explain. And embedded in those unexplained properties is almost certainly a deeper understanding of the solar system's relationship with the interstellar environment that will require new measurements, new instruments, and new theoretical frameworks to fully reveal. The data has given us the outline of a question so large and so fundamental that answering it will occupy the next generation of heliospheric scientists for decades to come. And somewhere out there, in the dark beyond the heliopause, Voyager 1 is still travelling, still listening, still sending back its faint signal across 22 hours of empty space, carrying instruments we wish were different, in a direction we wish we could change, whispering answers to questions we are still learning how to ask. We have travelled a long way together tonight, from the familiar warmth of the sun, outward through the planets and the asteroid belt and the frozen worlds of the Kuiper belt, through the termination shock where the solar wind stumbles and slows, through the churning turbulence of the heliosheath, across the heliopause where our star's direct influence finally yields to the interstellar medium, and into the cold, structured, surprisingly complex space beyond. We have looked at the ribbon that no one predicted and no one has fully explained. We have sat with the asymmetry of a bubble that breathes and shifts with the rhythm of the sun's own heartbeat. We have stood at the edge of the Oort cloud and tried to comprehend a gravitational kingdom that extends nearly a quarter of the way to the nearest star. We have considered the possibility of a hidden planet pulling on the architecture of the outer solar system from a distance so great that it has never been directly observed. And we have held the unsettling truth that the heliosphere's boundary is not a solved problem, not a closed chapter, but an open question at the frontier of human knowledge. All of that is real. All of it is confirmed or seriously proposed or actively investigated by some of the most capable scientists our civilization has produced. And I want to spend our last few minutes together, not adding more facts to that picture, but stepping back from it, letting it settle, and feeling what it actually means. Here is the thing I keep returning to, the thoughts that I find most difficult to let go of after spending time with this material. You are inside something. Right now, as you lie in the dark, as your breathing slows and the world around you grows quiet, you are inside a bubble, an enormous, dynamic, continuously generated bubble of charged particles and magnetic fields and solar influence stretching more than 11 billion miles in every direction from the sun. The heliosphere is not out there somewhere, distant and abstract, a thing that scientists think about in laboratories. It is here. It surrounds you completely. Every breath you have ever taken, every moment of your life, every experience you have ever had, every human being you have ever loved, every civilization that has ever risen and fallen on this planet, all of it has happened inside this bubble. The heliosphere is not a feature of the solar system. It is the solar system in its fullest, truest sense. And we live at its warm, sheltered centre. And it is alive. Not in the biological sense, not in any mystical or unscientific sense, but in the most literal physical sense of the word. The heliosphere moves, it breathes, it expands during solar maximum and contracts during solar minimum. It responds to the pressure of the interstellar medium pressing in from outside, shifting its boundaries, reorganizing its internal structure, adjusting the thickness of the heliosheath and the position of the termination shock in response to forces that originate light years away. When a distant supernova altered the local interstellar medium millions of years ago, the heliosphere felt it. When the solar system entered the local interstellar cloud tens of thousands of years ago, the heliosphere adjusted. When a solar flare erupts on the surface of the sun, the heliosphere responds within days. It is a system in constant dynamic exchange with its environment. Never static, never finished, always negotiating its shape and its properties with the cosmos around it. It is, in the most meaningful, non-metaphorical sense, alive with physics. What moves me most about this, when I sit with it quietly, is the question of protection. The heliosphere has been shielding the inner solar system from galactic cosmic rays for 4.5 billion years. Long before the Earth had an ocean, long before the first organic molecules assembled themselves into something that could be called life. Long before the first cell divided, the first photosynthetic organism released oxygen into the ancient atmosphere, the first fish pulled itself onto land. Throughout all of that, the heliosphere was there, doing what it does, breathing with the sun, pressing back against the interstellar medium, deflecting the cosmic ray flux, holding the space around our planet in a condition hospitable to the long, slow, improbable experiment of biological complexity. We did not know it was doing this. No living thing on Earth knew it was doing this until a small group of human beings in the second half of the 20th century began to piece together the picture from measurements and mathematics, but it was doing it regardless. The universe did not wait for us to understand it before it arranged conditions for us to exist. There is something in that thought that I find both humbling and, in the quietest way, comforting. We are small. The distances we have travelled through tonight are so vast that even the numbers fail to convey them adequately. The solar system is a bubble in an ocean of interstellar space that stretches across 100,000 light-years of galaxy, which is itself one of hundreds of billions of galaxies in the observable universe. The scale of what exists is so far beyond the scale of what any human mind can genuinely comprehend that the honest response is not confidence, but awe, complete, wordless, sustained awe. And yet here we are, small enough to fit inside a single cell of this cosmic structure, and intelligent enough to have sent 2 machines the size of a small car across 11 billion miles of space, and listened to what they had to tell us. The universe made us, and through us it looked at itself. We are the universe noticing itself. That is not a poetic flourish, it is the most accurate description I know of what a conscious being in an evolving cosmos actually is. Voyager 1 is out there right now. At this moment, as you settle into sleep, it is moving through the local interstellar medium at roughly 38,000 miles per hour, carrying a golden record inscribed with sounds and images from Earth, a message sent by our species into the dark on the chance that something, somewhere, might one day find it. It is moving away from us at a speed that feels enormous by human standards and is essentially motionless by cosmic ones. It will take Voyager 1 roughly 300 years to travel the distance of a single light-year. The nearest star is more than 4 light-years away. It will never reach another star, not in any time scale meaningful to human civilization. It will drift through interstellar space for millions, perhaps billions of years, long after the sun has expanded and swallowed the Earth, long after our solar system has changed beyond recognition, a small golden artifact of a species that existed briefly on a small rocky planet inside a bubble of solar wind in an unremarkable arm of an ordinary galaxy. And somehow, the thought of that does not feel sad to me. It feels right. It feels like the truest thing we have ever done. We reached the edge of our home and sent something across it into the unknown, not because we expected to be heard, but because we needed to reach, because reaching is what we are. Thank you for joining me on this journey tonight. Thank you for staying with me all the way to the edge of the solar system and back. If what we explored together moved you or surprised you or gave you something to carry into your dreams, please take a moment to like this exploration or subscribe so we can keep making these journeys together. Your support is what makes this possible, and every curious mind that finds this channel makes the community richer. Now let the scale of it all settle gently around you, like something vast and soft. You are inside a living bubble of starlight, drifting through an interstellar cloud, orbiting the center of a galaxy that contains more stars than there are grains of sand on every beach on Earth. The next time you step outside on a clear night and look up at the stars, remember that you're not just looking out into the universe. You are standing at the center of your own corner of it, sheltered by an invisible shield that has protected life on this world for longer than imagination can reach. Sleep well tonight. The heliosphere has you. And somewhere out beyond it, two small golden machines are still moving through the dark, still listening, still carrying our curiosity into the unknown. Good night. Keep looking up at the stars.